sample buildings, and here you see the link that I mentioned before. So you take this link and then you use the username and password that I just gave you to access the lecture notes. And then you get them here. And we are now jumping over 3.5. So that is what I mentioned before when I got the question. So that is what I asked you to read if you have not yet had that before, and to train it then in exercise 2. For those who have already had it, TP 4280, introduction to CFD, it would be a nice repetition. So then we can move on to the next part. What we have seen now in chapter 3 that we just did was the finite volume method for the heat equation. That is a parabolic problem, and the physical property that we have been investigating is the heat flux of the boundaries. There we had to approximate derivatives, giving us essentially the heat flux over the faces, using the cell averages. And then we saw how we could do that. And now we will move on to another problem that is also central in heat transfer and in fluid mechanics, that is transport, simply transport. And that is giving us the finite volume method for the one-dimensional linear advection equation. So that will now be chapter 4. The finite volume method, I used directly this acronym for the one-dimensional linear advection equation. So we assume that we have now, for example, we could have a pipeline, and there we have gas or liquid flowing. We make again the assumption that the cross-sectional area is constant, and we assume that the axial direction is the x direction. So that is our coordinate system. So we make then the following assumptions. We assume that the cross-section is constant, also the area is constant. We assume that we have only a dependence on x coordinate and time. So that means in each cross-section we have constant value. So that means our temperature that we want to investigate does not depend on y, and it does not depend on z. So that means we have only a dependence on x and t, the axial coordinate and time. We assume that the thermal diffusivity, that means also we would say the thermal conductivity, is 0, so that we don't have heat conduction. And we assume that we have the viscosity 0, so we have no heat production or dissipation by viscous effects. They are excluded. And we shall assume that we have a flow moving with a constant velocity u. So we have a lot of assumptions. So that means we have some liquid in here, or some gas that is moving with the velocity u. And that is our control volume, omega p. And we again assume that the left boundary, the western boundary is xw, and the right boundary of the cell omega p is the eastern boundary xe. And then the incompressible energy equation simplifies a lot. So the incompressible energy equation simplifies and if we look at it in integral form, then we can write it in the following way. Let's first think what will be left. We've already argued when we do this, we eliminate heat conduction. When you eliminate this, we eliminate the heat produced, dissipated by viscous effects. And if this is constant, things get simpler, but we will nevertheless have some convection part. And what will be left, actually, will be then essentially the time derivative of the temperature. And in our case, and for this simple case, we just integrate then from the western to the eastern phase. And what will be left will be the flux of temperature over the right and the left boundaries. And that will be the convective flux will be ut. And that will be then at the eastern boundary at a certain time t, and minus ut at the western phase at a certain time t. And that will be 0. And if we do that here, then it will be depend on x and t. So that would be then the integral form. I gave it here a number 0. So it means only convection or advection. Only that means transport is involved. The temperature that we have will just be transported. It will not change. If we had heat conduction, it would change by the effect that you have maybe already seen in exercise 1, so that we get a smoothing effect and the discontinuities will go away. But we don't have this. So if we have a discontinuous initial profile for the temperature, it will just be transported without change. And when we write it in this form, we assume again that this is the exact solution. So we don't make any assumption at the moment. It is like we did for the heat equation. In the beginning, we assumed that we have the exact solution. And we just write the form here now, first an integral form, because that is the form that we will use for finite volume discretization. In differential form, then we will have the following. That is what you probably know. That is the dt plus the space derivative of ut dx is equal to 0. So, and since u is constant, we can simplify that. In our case, u is constant. Then we get, as the differential form, we can put the u outside the derivative because it's constant. And then we get t, time derivative of temperature, plus the constant velocity times the space derivative of temperature is equal to 0. And that is what is usually called the 1D linear advection equation. Sometimes it's also called the 1D linear convection equation. There are different names for it, but that is probably mostly used. So what do we have in general? It is like we had also for the heat conduction problem. In general, we have initial and boundary conditions that we have also here. We have some initial temperature profile and we have some boundary condition. We start with the initial condition. For the initial condition, t of x0 is equal, we call it again t0 of x, we can give the exact solution directly. The exact solution of the linear advection equation reads the following. That is good to know. And that is that t of xt is equal to the initial condition, t0, evaluated at x minus ut. So that is the exact solution of the 1D linear advection equation. But if you don't believe me, and I think you should not do that in the beginning, you should try it. You take that, insert it in here, and make sure that that is really true. So check it by inserting it into the PDE. And this here already indicates something interesting. Everywhere where x minus ut is constant, we have the same temperature. So if we start at some point for an initial condition and we are then on a line where x minus ut is constant, we have the same solution. So and that gives rise to considering certain curves in time-space where we essentially know something about the solution by this. And these curves are called characteristics. So on characteristics, so this will be some repetition for the people from TP 4280, Introduction to CFD, but it's, I think, useful. So these characteristics are then defined by curves x of t, so then x is no longer an independent variable, but it's dependent on t, and its slope is given by the constant velocity u. So that means these characteristics in this case that we consider for the linear advection equations are then curves that we can characterize by x0 plus ut. So if we have such a dependence of x on t, we see the x dt is u. So these curves then are, according to our definition, are then the characteristics. And the x0 can be any value, any real value. So on these characteristics, we can see that the PDE1, that is our linear advection equation, can be simplified to an ODE. And to the following ODE. ODE is just the acronym. PDE is partial differential equation, and ODE is ordinary differential equation. So in PDE we have not just one independent variable involved, but in our case we have x and t, but ODE we have just one, in our case t. And this ODE that we get, that is the claim, is the following, that we have the derivative of x of t, t. So that means now the arguments both depend on t. This is clear, but here now, since x is no longer an independent variable, it's now dependent on t. So then this is just a function of t. So we can do the first derivative with respect to t, and the claim is that this is 0. So if we have an exact solution and we are on the characteristics, then this is the claim. And that means that the temperature is constant on characteristics, because if we are on such a line defined in this way, it says that it does not change. And that means that the temperature is then constant on characteristics. we can prove that. So we assume that we have the exact solution of the linear advection equation, and we want to check whether this is true, what we claim there. So we give an argument now for this claim. So what we do is we derive the T dependent on X and T. This is our exact temperature, but now dependent on X of T, which is then defined, for example, in this way. And T. Then we can use the chain rule, because we have a dependence now both on X and T, and X is in itself dependent also on T. So if we take first the derivative with respect to T, that is then the partial derivative, then we will take the partial derivative with respect to X, but then we have also to take the derivative of X with respect to T, because that is dependent on T. And then we use the fact that we are assuming that we are on a characteristic. That means that this slope is equal to U. So it means this is equal to U when we are on a characteristic. And then we have assumed that T is an exact solution, or the exact solution of our linear advection equation. And then we have first time derivative plus U times first space derivative, and that is then 0, because then we can use the PDE, the linear advection equation, that is 1. And that tells us then that what we assumed here, that is correct. So if we are on a characteristic, then the temperature does not change. So what does that mean? If we look now first in the xt diagram, where t is time, so the xt diagram, and we assume that we have, say, the origin here, and that we are at some point, that we start at some point, then we can always write the characteristics there. So the characteristics will be then u0 plus ut. So the x0 will be essentially then the distance, if that is 0, that will be then our x0, and the slope, that will be given by u. So the dx dt, I have to say that this is x, so the dx dt is then the slope. And so that is the slope here, dx of t dt is u. So if you have here a delta x and you have here a delta t, then the ratio of delta x to delta t is then the slope. So be aware of that we look here at the tx diagram. But this is the slope dx dt. Anyway, and we have this slope all over, because the u is the same. Wherever we start, which x0, it's just the same. We have the characteristics will all have the same slope. But what we know is when we are, for example, at a point, let's say we are at xj, and we want to know what is the solution at xj at a certain time instant. So that is the, say, the Tn. What is the solution at this point? Then we know that the temperature is constant on the characteristics. So that means what we want to know here at this point on the characteristics, it will be the same as here at this point. And what is this point? If this is xj, what is this point? We can find that out by the slope. We know that the slope is u, We know this time is Tn. So that is Tn. And we find out that this here then is u times Tn. That is u Tn, this distance. So that means the point that we are interested in is then the point xj minus u Tn. There we have to take the initial condition, and then we know the solution at any point on this characteristic. So that means that the temperature at this point then is then let's see if we can get that the T at this point, that is then the T of xj Tn that we consider here, that is then the T that we have at this point for the initial condition, the T0, and that is then the xj minus u Tn. So then we know the solution at any point on the characteristics. We just have to go down to the initial condition, and then we get the solution. So what is the consequence of that regarding our solution? So we now assume that we have a given initial condition. Say I assume in the example that we have a sign. That would be our initial condition here. Now I remove this here. So the value that we had here, that was the xj minus u Tn. That was the value that we had here. But now we want to look here at t. And we look here now first at the t of x0. That is the initial condition. That is the one that we have here. And now we want to let this thing move. We want to go to see what is then happening at the time Tn. So then every value will move just this distance to the right. So let's see, try to indicate that. So if we are at this point here, this crest here, that will move just to the level where we are here. We want to have this time, so it will move here. So it is that we see, I try to have a measure here. Well, it's roughly 1 page, little less. So this point will move roughly to here. This point will roughly move to this here. This will roughly move to this here. And this roughly move to this here. So that means after a while, so we have then, so this point will move here. This point will move there. And that point will move to that, there, and so on. So after a while, we can expect that we have something like, try to get a sign out of that. Something like that. It has simply been shifted to the right. By this distance that we said in our case would be the u Tn. So then the yellow curve would be the solution T of x Tn in our example. The profile has not changed, it has only been transported the distance u Tn. That's all. So therefore, if we know the initial condition, then, and we have it defined for all x, then we know the solution for any time. So that is just means that we have just a transport of the profile without change of the form. What can we learn about boundary conditions? See, we have not discussed boundary conditions yet. Here we also see when we are when we want to know the solution at this point here, then we go in the xt diagram with the time, x space, t time, and we go back, and then we find this point. So in that case, we just go back in time, and then we are at the initial condition at a certain x location, and then we take the value of the x location of the initial condition there, and we have the solution. You can do that for any point, and in that way we have the exact solution. Now, boundary conditions. So that is very important because we usually cannot compute infinite domains. We are finite also in the computer. So we have to limit our domain, and we have to, if we want to compute the large or the whole space, we have to have artificial boundaries. So now we have gained the xt diagram, but now we assume that we are looking at a certain domain which is bounded by xa and xb. So this is our flow domain where we want to investigate the propagation of the temperature. Again, we assume what we do here, that u is positive. That was implicitly meant whereby here, when we have the characteristic like that, then if this is positive, then they go this way. If they are negative, they go this way. So that was already implied here in this picture that u was positive. So we continue with this discussion that it's positive. So then the characteristics will look similarly. They will all be parallel, and their slope will be given by u. So then we have again that the slopes, all of these characteristics, is equal to u. It's positive. Now let's look at the boundaries. So here we have the boundary at the right. We have also t here. And if we are inside the domain, for example, at a point here, then we can go back to the initial condition, get to the initial condition, and then we have the solution in the way that we discussed. So that is no problem. That is clear. But what is if we are, for example, at a point here? If we are at a point here, this is our x location, then we will hit the boundary. We cannot get to the initial condition because the boundary, our domain ends there at xa. So what does that tell us? We cannot determine the solution by the initial condition in that case. We need a boundary condition. We need to tell what is the temperature at the left boundary at this time. Otherwise, we don't know what is going in. So that means at the left side of the domain, if u is positive, we have to give boundary conditions. So boundary conditions are needed. And that means that we have to give the t of xat has to be prescribed. Has to be given or prescribed, as you like it. So that is really then needed. So at the left boundary, if u is positive, we have to give what is getting in, which temperature is getting in at the left boundary. Otherwise, we cannot solve the problem. If we know that, then we know the temperature value here, and then we know the solution. Then it is given by the boundary value here. If we are at any other point, we just go to the boundary and find the value of the temperature at the boundary, and then we know what is happening. So in either case, at any point then in the domain, and the distinction is actually this line, the characteristic starting at xa. to the left, everything is determined by the boundary condition on the left, at the left boundary, and to the right, everything is determined by the initial condition. Okay, now the question, what about the right boundary? Can we say anything there? For example, if we are at this point here, at the right boundary, do we know anything? Yes, we do. Because this is on a characteristic that goes back either to the initial condition in this case, or if we are far off, if we are far away, then we will go back to the left boundary. In any case, either by the initial condition or by the left boundary condition, we will know what is at the right boundary. That means no boundary condition must be given at the right boundary, because we know already what is going on. So that is very important. No boundary condition is needed. And it should not be given, because if we give a boundary condition here, then it contradicts to what is then given by the value here, things will not work. So then we will have not a well-posed problem. So the solution is determined. So at the right boundary, solution is determined by initial and boundary conditions. By initial and left boundary conditions. So that is what is the reason for that. But this is important. So if you have such a problem where u is positive, check whether in that case the temperature profile is leaving the domain. If it is, no boundary condition needed. If you give a boundary condition there, you will get trouble. So that is very important to understand, and for yourself I suggest you to think yourself what is happening for u smaller than 0. So then you will understand it. So that what we have now discussed is mathematical theory. And it is, as we have just seen discussing the boundary conditions, extremely important for solving the problem also numerically. So, because it tells us where we need to give boundary conditions and where not. So now we want to solve it using the finite volume method. Again, we introduce a cell average. So with the cell average, as we had defined before, for the heat equation, we also do that now for the linear advection equation. The definition is just the same. It's 1 over the length of our control volume, that is our interval from the western to the eastern face, and we integrate from the western to the eastern face, t of x t dx. So that is our cell average in the cell P. And the delta xp is the distance from the western to the eastern face. So with that cell average, the integral form that we denoted by 0 before of the linear advection equation of the 1D linear advection equation can be expressed as, and then we use similar arguments as we did for the heat equation. So we have the time derivative of the integral of the time derivative from xw to xe, and then introducing the cell average, we get the length of the control volume, delta xp, times the time derivative of the cell average in the cell P. So we take then the average of that, but it's then the exact value of T that we have here, giving us the exact cell average. And then we have the convective fluxes at the eastern boundary minus the exact convective flux at the western boundary. So all we did was that we had before, all we did was to replace this integral that we had before of the time derivative of T of the temperature by this expression for the cell average. So that is then that equation 5. And it is then this equation that we are going to approximate. At this point, everything is exact. The cell average is the exact cell average. And this is the exact value of the convective flux at the eastern and western phase. So, in the finite volume method, the UT, that is the convective flux at eastern and western phases, are approximated by neighboring cell averages. So thereby we introduce approximations. And so the T hat P is therefore in the finite volume method approximated by what we denote by simply TP. So we skip the hat for indicating the exact cell average, because when we do these approximations here, we have to approximate that. And then we can only do that when we approximate the cell averages. Okay. So then in the finite volume method for the linear advection equation, for the 1D linear advection equation, we then get, if we use the notation with P and so on, we get then the delta xp. Now it is then the finite volume approximation of the cell average, so I have removed the hat from here. And then we have to get approximations to these convective fluxes. And we indicate that by just writing an index. So that is now supposed to be an approximation of the convective flux that is here. This is the exact one. But here we use no approximations. And also we use an approximation for the western convective flux. If we use the index notation, we will call the cell P for J. Then we will have the time derivative of Tj, and we will have the convective flux Ut, again at J plus 1/2, and west is at J minus 1/2. Is equal to 0. So that will be then our notation, and the whole catch in finite volume method is the way we approximate these convective fluxes. So that is then the whole catch. To indicate the discussion that we have there, what we are assuming is similar picture as we did for the heat equation regarding the control volumes. And also the notation is just the same. We just focus on some interior cell. Here we have, and we say we have here the P. That is one way, that is the midpoint of the cell omega P. That is one notation. The other is to call it xj. We have a neighbor, that is the eastern neighbor, that is, would be the index j plus 1. And we have a western neighbor with the index j minus 1. And the faces are either w or j minus 1/2, or little e and j plus 1/2. And we will locate our cell averages again at the midpoints. So we have here then, this would be again the tj. Here we would have the tj minus 1, for example, if we just pick some examples, and here maybe the tj plus 1. And based on these averages only, we'll have to determine the convective fluxes at the faces. So we can say that the finite volume methods differ in the way these convective fluxes are approximated. So that is the bottom line, and what we are going to then to see next week will be different approximations, which gives us the different finite volume methods. So the finite volume methods differ in how, in the way in how the convective fluxes that is in our case the index notation utj plus and minus 1/2 are approximated. And what we can immediately see is a central approximation would be just taking the average, for example, of these two guys, taking the average, and here taking the average here. But we shall see that is not a good choice. Okay, so we stop here, and I would like to remind you of the deadline for exercise 1, that is on Friday. Please respect the deadline. So Sondra, the teaching assistant, would like to have your answers to exercise 1 by Friday. And you can read the guidelines, so try to zip it to one file and submit it via its learning. And we'll have another guidance tomorrow evening from 6 to 8 in R54. Otherwise, we'll continue on Monday with the feedback on exercise 1 and ask questions on exercise 2 at 6 to 8 in the evening in R54. And the next lecture is on Tuesday next week, 10 to 12 here.